So here I have two collision cars. They are identical except for color. They are both 0.5 kilograms or 500 grams. Right. I'm going to push these collision cars towards each other. Okay. Whitney. Caleb, thank you. I'm going to push the collision cars towards each other. And I want you to think about the impulse, how the impulse exerted on the two cars compare. Anthony, Eric, pay attention, please. All right. So, collision cars towards each other. Okay. Collision cars towards each other. Okay. Now, what do you guys notice about certain important quantities here?
Velocity?
What about the velocities?
They're not. Well, they're probably not exactly constant.
Probably not exactly constant.
Well, I mean, equal.
They're probably not the same.
And there's a piston on one.
Well, let's do a little exaggerated one. You guys ready? Slow blue, fast red. Okay. Ready? Slow blue. Oh, I came off track. Slow blue, fast red.
The velocity switch.
Slow red, fast blue.
Ready? Switch.
Slow blue, fast red. Okay. So, what can you guys tell me about the impulse here?
Let's swap it.
Blue stopped. There's even a even better case. Very slow blue. What happened?
Why I do that?
Conserve.
They transferred.
What transferred?
Their energy.
Hey, it's like the
Kinetic.
it's like the Newton balls,
We're not talking about kinetic energy here.
right?
Momentum.
Momentum. So what do you think
They go
transfer,
up.
Rex?
Their momentum.
Their momentum's transferred.
It's like the Newton balls.
So we call it Newton's cradle.
No.
Okay. So the red car, we're going with what Locke said, and Rex transfers its momentum to the blue car, right?
Yeah.
So let's look at this situation. Red car's momentum is this way, right?
Yeah.
Blue car's momentum is this way, right? So now, after the collision, what happens to momentums? They switch directions, right? So what was that term you used again, Rex?
Newton balls.
Transfer.
Transfer momentum, right? So Newton's cradle.
The cradle balls.
Newton's ball.
Yeah.
The balls.
This is a conservation momentum experiment. Please stop saying that term.
What?
Okay.
Newton's
Balls.
Oh my gosh. Now, the way this works is the shiny spheres transfer momentum to one another. That's why you always see the same mass come off on either side. You see that?
Wow.
Now, what's going to happen if I use two spheres?
Kind of weird.
It's gonna hurt.
Two come out the other side, right? It's transferring what?
Momentum.
Momentum. Yeah.
Three.
What about three? What do you think?
It wouldn't work.
No, the one in the middle is gonna. Or no.
Oh, that's it. Four.
Four?
It's like magic.
Okay, 5 isn't very fun, so we're not going to do 5.
Do two at the same time. It's really cool.
Two at the same time.
Okay.
That reminds me of
I
the
meant
episode
two,
of
like
SpongeBob.
two twos. You know.
That reminds me of the episode of SpongeBob where Gary's eyes stick
All right.
Oh yeah.
and the bubbles going blue.
Oh yeah.
Okay, so what's happening here is the cars are transferring momentum to each other, and Newton's cradle's transferring momentum, right?
Yes, balls.
So let me draw the two cars. Now my red marker is dead, so I'm going to use a green marker instead of red. So where you see the green car, that's really supposed to be the red car. Okay? Whitney, pay attention, please. So, what color is this car?
Red.
Thank you. What color is this car?
Blue.
Blue.
Green.
Okay. So, that velocity was 0 initially, right? This velocity was not 0. I know it's green. Like I know it's green, but I don't have a red marker.
Budget cuts.
Okay. No, actually, I don't buy red markers because red markers are the toughest to see when they're starting to work.
Oh, like this color. I thought it was yellow.
Why don't you buy just black markers?
Because then I can't multicolor pictures.
Well, like
Okay.
black and blue.
So, how does the velocity here compare to the velocity there?
The same.
Well, it's the same. Because you guys said it transferred the
Momentum.
momentum. So what was this velocity?
0.
0. Okay. So what can we say about the change in momentum for each car?
What do you mean? What do you equal?
How is the change in momentum for this car, for the green car, sorry, the red car, related to the change in momentum for the blue
It's
car?
equal.
It's equal. Okay, because their masses are identical, right?
Yeah, sure.
So this one has a certain amount of momentum here, and that one has the exact same momentum there, right? Right? So we can say that in... Now, is it just this collision, or do you think it was any collision?
Any.
Because when we then set the blue car and the red car heading towards each other to start, they bounced off going the opposite directions, and how did their velocities compare?
Well, I don't know.
Probably different mass.
They're probably they were the same, right? If I sent the blue and the red car towards each other at identical speeds, right? They bounce back at identical speeds. But remember when I had the slow blue and the fast red, right? The fast red hit the slow blue. The blue went fast and the red went slow. So they like transferred their speeds, right? But it's really not their speeds that are transferring, it's their momentums. And the reason why the speeds are identical is because the masses are the same. Right? So not just in this collision, but in any collision, both objects have the same change in momentum. Okay, that's what that means. For our collision cars, the change in momentum for the red car equals the change in momentum for the blue car. Now in your notes, I want you to title this impulse and N3. What's N3 stand for again? Uncertain law. So you're probably saying, why are we saying impulse and N3? We're just talking about impulse, right? Right?
Yeah.
Wesley, Eric, that's not how we pass class, guys. Earbuds out. Pay attention up here.
Did you really call him Wesley?
Oh, Anthony. Goodness, sorry, Anthony. Okay. All right. So, how does the force exerted on the green car, the red car, compare to the force exerted on the blue car when they collide? They're equal, right? The force exerted by the red car is equal to the force exerted by the blue car. Is that the case when the red car is going faster than the blue car? Is that the case? Is that still the same?
Yes.
Yeah, these
Yeah.
are still the same.
What about if they're going towards each other at identical speeds?
Yeah.
What about if one's stationary and one's moving?
Yes.
Yes.
Yeah. Newton's third law says every action has the equal and opposite reaction, right? So if the red car pushes on the blue car with some force, the blue car pushes back on the red car with the same force, right? Right? Now, what do we know about the length of the collision? What do we know about the length of the collision? Is the time the same for each car?
Yeah.
Yeah. They both experience the same time interval, right? So if I look at this problem instead of from a momentum standpoint like we started out looking at from, if I look at it from a force and time interval situation, we'll get a similar result. So if this is the blue car and this is the red car during the collision, remember the centers of masses, so the little spread apart? The red car pushes on the blue car which way? To the right.
Wait, did it really not happen?
Right? With some force. The blue car pushes on the red car which way? To the left. With a force that is equal and opposites to the blue car, right? Right? So what that means is that the F delta T over here. F delta T for the blue car is equal to the F delta T for the red car. Okay? Now that's just in terms of magnitudes, right? Their directions are opposite, aren't they? So that means if I'm going to add my vectors here, one of these has to be negative. If I'm going to add these vectors here, then one of these has to be negative. But what these both show us is our idea about momentums transferring agrees with Newton's third law. Does that make sense? Because the cars push on each other with the same force for the same time interval, we know their change in momentums are the same. Does that make sense?
Yeah.
Remember, this is J, right? Impulse, right? And impulse is the change in momentum. Okay? So the impulse of the red car equals the impulse of the blue car. The impulse of the red car equals the impulse of the blue car. And the reason why one is negative is because they're going in opposite directions. Does that make sense, guys? Okay. So the big point. In any collisions, both objects have the same change momentum. And that's a result of
Physics.
Newton's third law. The reason why they have the same change momentum is because the forces are equal, right? Newton's third law, equal opposite force, and they have the same time interval, right? Same time interval means same change momentum, because force times change momentum or change in time is the change in momentum. Does that make sense, guys? Yeah. Are there any questions?